We are going to learn about establishing relations including trigonometric ratios using the basic trigonometric identities. Look at this example. We are required to show that cosine to the power 4 theta minus sine to the power 4 theta over cosine squared theta is equivalent to 1 minus tan squared theta. Here we do not only simplify. We need to equalize the first form with the second form. Pay attention that with this kind of questions, we start with the form that needs more work. 1 minus tan squared theta is less complex than the first form. So let's start with the left-hand side, and we need to make it equal to the right-hand side. In this way, we verify the relation. We will start with the left-hand side. The work will begin with the numerator. The numerator has the same form as a to the power 4 minus b to the power 4. This reminds us of the difference of two squares. A squared minus b squared, it is a minus b multiplied by a plus b. In other words, to find the terms here, we do the square root of the first and the second term. Now, in the same way, a to the power 4 minus b to the power 4, we can say that it is a squared raised to the power 2 minus b squared raised to the power 2. This is the same as the difference of the two squares. A squared minus b squared multiplied by a squared plus b squared. We apply this on the cosine and sine. Cosine to the power 4 theta, if we do the square root for it, it is cosine squared theta. As for the sine raised to the power 4, it is sine squared theta. And we know that cosine squared theta plus sine squared theta is equal to 1. This is the Pythagoras theorem in trigonometry. Now, let's write this. Cosine 4 theta minus sine 4 theta, just like the above, it is cosine squared theta minus sine squared theta multiplied by cosine squared theta plus sine squared theta. This is done by using the difference of the two squares. For this relation, we know that it is equivalent to 1. So we are multiplying all of this bracket by 1 to get cosine squared theta minus sine squared theta. Okay, now let's write the relation in the fraction. All of this is divided by cosine squared theta. As we said, this is equal to 1. Cosine squared theta minus sine squared theta over cosine squared theta. Now we finished with the difference of two squares and the factorization. Okay, now by using the concept of the fraction, we can separate the denominator for each numerator. So, cosine squared theta over cosine squared theta, this is the first part, minus sine squared theta over cosine squared theta. Okay, now for this value, we have sine squared theta over cosine squared theta. We can put the power 2 outside. Inside we have sine theta over cosine theta. We have a rule that says sine over cosine for the same angle is equal to tan theta raised to the power 2. Thus it is tan squared theta. Cosine squared theta over cosine squared theta is 1. So 1 minus, we deduce the answer for this, it is tan squared theta. As you can see, this is the same as the right hand side. Thus, this is verified. As a recap, we relied on the part that had more calculations. We factorized the numerator like this. We made use of the concept that cosine squared theta plus sine squared theta is exactly equal to 1. Then we separated the numerator because there is a subtraction between them and they are divided by a common denominator. Then we made use of the concept that sine over cosine for the same angle is equal to tan, and we organized it in order to prove that it is the same as the right-hand side. Look at the book. When you have to prove an identity like this, you may quote the basic identities like sine squared plus cosine squared is equal to 1. And usually the best strategy is to start with the more complicated side, here the left-hand side, and try to produce the expression on the other side. The numerator can be factorized as the difference of two squares, which is sine squared theta plus cosine squared theta equals 1. Finally, we use the concept that sine over cosine is equal to tan. In the same way, you can solve these exercises on your own. Sometimes you may need to expand or factorize in order to solve.